Hi, this is Dane Quinn from the University of Akron, and today I'll do an example dealing with particle dynamics. We have a block of mass m that's released from rest so that the initial velocity here is equal to 0 and slides on a rough surface, so there is some coefficient of friction, mu, and the surface is inclined with respect to horizontal at an angle of phi. So what I'd like to know is the minimum angle of inclination, so the minimum angle that we can tilt this surface, and I'll call that minimum angle phi star, that's necessary for the block to slide. So if phi is greater than whatever this critical angle is that we solve for, then the block will slide down the plane. If phi is less than this critical angle, then the block should just remain stationary or stuck. Then, if phi is greater than whatever that critical angle that we find is, I'd like to determine the acceleration of the block down the plane. Let's begin this problem by looking at the forces that act on the block. We certainly have the weight from gravity, and so we'll represent that force by W. And then we have two other forces. One of them is the normal force that acts between the surface and the block. So we will identify that force as N. And then finally, we have the friction force. Again, between the surface and the block. And the friction force is the force that resists relative motion. So the normal force is going to be normal to the surface, while the friction force is going to be directed along the surface. So these will be the forces that act on the block. Now, if I look at the motion, the block should slide up and down the plane. So that our next step is to identify coordinates and directions as well as kinematics. And we'll start with coordinates and directions. Let's define I and j as horizontal and vertical. And then, because the motion of the block is along the plane, it makes sense to define a direction along the plane, and we'll call that E1, and then a direction that is perpendicular to that, or normal to the plane, E2. And here, the angle phi describes the orientation of E1 with respect to I. As a result, we can relate these directions to one another. So in particular, looking at E1, we find that's cosine of phi in the I direction minus sine of phi in the j direction, while E2 is sine of phi in the I direction plus cosine of phi in the j direction. Now relating I and j to E1 and E2, we find that I is equal to cosine of phi in the E1 direction plus sine of phi in the E2 direction, while j is equal to minus sine of phi in the E1 direction plus cosine of phi in the E2 direction. When it comes time to look for appropriate coordinates, well, coordinates are measurable quantities that describe the configuration of the system. So what do we want to measure to identify where the block is? Since the block moves down the plane in the E1 direction, let's measure the displacement of the block in the E1 direction. Right, so we'll identify some reference origin, say here, and then the displacement of the block will be measured with the quantity x. As a result, we can determine the kinematics of the block, which amounts to finding the acceleration in terms of the measured coordinates and directions. So here the acceleration of the block is x double dot in the E1 direction. If I can solve for x1, then I can find the requested acceleration of the block when it's slipping down the plane. Again, at this point in the problem, I don't know what x double dot is, and that's fine. What I'm trying to do here is relate the measured coordinates to the acceleration. Right? So the acceleration of the block is given as x double dot in the E1 direction. The next step in our procedure is a free body diagram. So we'll look at those forces. Again, we identified them on the previous slide. We had the weight, we have the normal force, and we have the force due to friction. So the weight is minus mg in the j direction, while the normal force has a known direction but unknown magnitude. So we'll say n in the E2 direction. Finally, the friction force I will represent as minus Fr in the E1 direction. So I don't exactly know what the friction force is yet because I haven't said if the block is sticking or slipping. So I'll just represent it as some unknown quantity, and then as we come to the point in our problem solution that we're ready to determine and distinguish between stick and slip, we'll specify the friction force to be the appropriate value. But these are the forces that act on the block. So now, applying linear momentum balance, or sum of the forces is mass times acceleration. This is the equation of motion. These are the laws of mechanics that govern the behavior of systems. Then we can basically look at our free body diagram to identify the forces, and we've already written the acceleration in terms of the coordinates. So the acceleration, and in particular the right-hand side, is mx double dot in the E1 direction, while the forces that act on this system are minus mg in the j direction, plus n in the E2 direction, that's the normal load, minus the friction force, Fr, in the E1 direction. So here we have linear momentum balance as applied to the block. Now this is a vector equation, so we have two scalar components. I could take components in the I and j direction, or I can take components in the E1 and E2 direction. There are two reasons that I want to take components in the E1 and E2 direction. One of these reasons, quite honestly, is that there are more terms in the E1 and E2 directions, so if I take things in the E1 and E2 directions, I only have to transform this one force as opposed to these three forces if I were to do it in the I and j directions. However, an even better reason is that if I look at my unknowns, I don't know the acceleration, I don't know the normal load, and potentially I don't know the friction force. So all of the unknowns are nicely split in terms of the E1 and E2 directions, while the weight is completely known. So taking components in the E1 and E2 directions will take advantage of the fact that the unknowns are nicely split in those directions. So really what we need to do is write J in terms of E1 and E2. But we've already done that here. So I'll take this expression for J, I'll use it here, and then I'll find components in the E1 and E2 directions. This becomes, in the E1 direction, mg sine of phi minus Fr in the E1 direction. Then in the E2 direction, I have n minus mg cosine of phi, E2, equals mx double dot in the E1 direction. So this is linear momentum balance written in terms of the directions E1 and E2. Finally, taking components in these directions, we find our two scalar equations. So looking at the E1 direction, we have this coefficient equals the coefficient on the right-hand side. Or mg sine of phi minus the friction force equals mx double dot. Then in the E2 direction, we have n minus mg cosine of phi equals 0. So we can easily solve the second equation for the normal force. In particular, the normal force is mg cosine of phi. And this is something that obviously came from our application of linear momentum balance. We didn't have to just sort of guess what the normal load is. We were able to solve for it. Now let's look at the two cases, stick versus slip. So if the block sticks, then x double dot is equal to 0. That's what it means to be stuck. The block is not moving, so the acceleration vanishes. And looking at the equation in the E1 direction, we have mg sine of phi minus fr equals 0. So the friction force is mg sine of phi, provided the block sticks. We ask for the critical value of the angle for which the block transitions from stick to slip. So that's going to be determined by our friction inequality. So notice that the magnitude of the friction force must be less than or equal to mu n. This is part of Coulomb's friction. So now, if I look, the magnitude of the friction force is mg sine of phi, and that has to be less than mu times mg cosine of phi. As a result, and here assuming that phi is positive, so that this quantity is always positive, this implies that tangent of phi must be less than or equal to mu. The critical angle occurs when tangent of phi star, again that's the critical angle, is equal to mu. So we can solve now for phi star and show that this critical angle is the inverse tangent of mu. Finally, if phi is greater than this critical angle, then the block slides. And when it slides, we know the friction force. In particular, Fr is equal to mu n. So we can go here and find that mx double dot equals mg sine of phi minus the friction force, which is mu, times n. And of course n is mg cosine of phi. So finally, we can solve for x double dot as g times sine of phi minus mu cosine of phi, provided of course that phi is greater than phi star, which we found to be the inverse tangent of mu. And as a result, we have solved for the acceleration. The acceleration finally is x double dot in the E1 direction, or g sine of phi minus mu cosine of phi in the E1 direction, provided the block slips down the plane. So let's draw a graph of the acceleration as a function of the angle phi. So we'll have some critical value of phi star. Let's assume that it's here. So if phi is less than this value, the acceleration vanishes. So the acceleration is essentially 0 all the way up to this value. And then at that point, the acceleration begins to rise. And it does so kind of in the following way. Notice that at phi star, the acceleration is 0. And then if phi star is equal to pi over 2, then the acceleration becomes simply g. Well, that makes sense. If the surface was vertical, the acceleration of the block would just be the acceleration due to gravity. Right, so we're able to draw and understand the acceleration of the block as a function of the angle of inclination of the surface. So that's it for this problem. We have looked at a very simple problem with friction, and we're able to distinguish between slip and stick in the resulting motion depending on the angle that we orient the surface. Well, thank you very much, and I will be back later with more examples.